Alrighty. So what we have up here is our exponential growth formula. It is almost identical to the ones we were working with yesterday. It's just that instead of having a base, we have this 1 plus whatever, or plus or minus whatever our rate is. Our rate needs to be as a decimal. That is critical. Do not put it in as a percent. It has to be as a decimal. It has to be in decimal form. As a decimal. I know it's written right over those words, but. There we go. As a decimal. It has to be as a decimal on there. So, other than that, it's pretty much the same as what we have. We just have to figure out if we're doing growth or if we're doing decay. So we know whether we're using the plus or the minus. So when we're putting this equation together here for this story, we've got the population of Albany, Kentucky is growing at a rate of 2% each year. That's what annually means. And if the current population is 25,000 people, what's the population going to be in 5 years? How are we going to build this equation?
25,000
Mm-hmm.
times 1 plus 0.02 to the power of 5.
Yeah. So we're going to have our 1, and then since our population is growing, we're going to add our 2%, which is 0.02 to the power of 5. So we had our starting population that went here. That's our P, our principal. Our rate of 0.2, that was our 2% put as a decimal. And our T of 5. So I do recommend we simplify the inside the parentheses parts first, just because it's going to be really helpful when we get into doing things that involve logs for these when we're having to solve for stuff. So I highly recommend that we simplify this part first, 1.02 to the 5th. And then we can type it in the calculator. How many people are going to be in this town in 5 years? 27,600 and how many? 2. Even though there's decimals after it, why am I not including decimals? It's people. Do not throw random limbs into your town. It will probably affect the population in your town. I'm assuming that it will probably stop growing if you start throwing random limbs into town square. The population might change. If there's a random leg that shows up in town square, I would probably move. Okay? Questions on this one? Boop. Told you there's not much on them. But sometimes we don't have growth. Sometimes we have the value of a car, which this is an actual depreciation rate of a new car. Not every car, but a lot of them. You buy a brand new car for $23,000, and the second you drive it off the lot, it loses value of about 15% each year. So, what's the value of your brand new car after 3 years? So we're going to build our equation with the amount of our value, so the value of our account. What do we start with?
20,000.
Our 23,000. That is our principal. Hang on a second. That's our principal here, this guy. Oop, sorry, pen. Then we're going to have our 1 minus, because it's losing value, our 15%, but as a decimal, so our 0.15. to the power of 3. Again, I'm going to simplify what's in the parentheses before we type it into a calculator. Honestly, it's going to be really handy for us next week when we start working with these the other direction. Just to be in that habit. 23,000. What is 1 minus 0.15? 0.85. So we can really see here that my base for my exponential is smaller than 1. That's how we know this is decay. On the last one, my base was bigger than 1. That's how it was exponential growth. So since our base is less than 1, this is decay. So what is the value of my car after 3 years?
$14,124.88.
So in 3 years, which I said 3 while trying to write an 8, and that did not work well, it loses a lot of money, which is why you will always hear financial people say a car does not count as an investment. It is a tool. You need to have one. It is not an investment. You don't make money off of them. Unless you wait a very long time and it turns into a classic. And very rarely some pickup trucks don't lose value. But for the most part, a car is not a good investment. It's a tool. Got to have one. If you want one that makes your heart happy, absolutely go for it. But you won't make your money back on it. That's my little preach about don't buy a brand new car. Used cars. Let someone else pay for that depreciation. Buy a used car. Okay. So the next one's not in our story problems that I gave you, because it's not really a story. I'm going to give you an equation, and we're going to find some pieces. So now I'm giving you an equation. We're going the other way through it. I want you to tell me our principal and what is the percent of the rate change. So we're taking an equation like the ones we just built and working backwards. 3,000 is what we're starting with. This guy is our principal, that P, that starting amount. So that's our 3,000. Careful.
25.
So when we're looking for our rate change, we got to remember that this base comes from 1 minus something that equals our 0.75. This is, I'm going to switch back. They wrote it like, that's not what I meant. I meant the laser pointer. They wrote it like this and then simplified it. So we're trying to go the other way. I want to know what R is. Oh, that's meant to be a 5, not a 7. I'm so good at doing things while talking at the same time. I'm so good at it. So what is the decimal of our rate? 1 minus what gives me 0.75? 0.25. So what is the percent of change? 25%. There's questions like that on the homework. Identifying the rate that we change. Okay, so I wanted to practice going that direction because we get a little caught in that one. Okay. So questions on our simple interest where it's changing with an annual rate and things aren't too complicated, because then that works for some things like depreciations of cars. But things like bank accounts and savings accounts and credit cards, they're a little bit more complicated because they're going to use compound interest. It has a lot of the same pieces. We still have the amount. A is for the amount in our account. P is our principal or starting amount. R is still the decimal version of our rate. T is still our unit of time. N is our compound piece. So this is, again, we did do this in Algebra 2. So it's a lot of the same pieces. P is our principal, R is our rate, T is our time. N is how many times we compound per T. So it's really, really similar here. And we've got two questions about the same paragraph, just compounding it differently. So let's start by building our equation over here. So the amount in our account is, what are we going to start with? 4,800. That's our principal here. Then we're going to have our 1. Are we going to use plus or are we going to use minus? Plus, because she's earning interest. What's going to go on top of my fraction? 0.045. My rate as a decimal. So now we're looking for our compounding factor. So we have this one here, which is semi-annually. Think about a semicircle. 2. There's 2 parts of semi. Semi-annually is not used super frequently. The only time I really hear semi-annually is there's some stores that do semi-annual sales. And they'll do it twice a year. They'll do a spring sale and a fall sale. So semi-annually, when in doubt, think about semicircles. There's 2 halves. Unless you are really well versed in the sales cycles of some certain stores. So 2 is our n here. And then we also have our n up in the exponent again. So we're still going to have this 2 up here. But now it's going to be times what? Times our 20 years. So she's putting this money in the bank and walking away for 2 decades. Well, this will happen a lot of times if grandparents will open college savings accounts and they'll put a chunk in when someone's born and then they don't put more into it and or forget. And they go, oh yeah, I made that savings account. I should probably see how much is in it. Let's see how much is in it. So we're going to simplify things as much as we can. So our amount is, we can do our 4,800. We can simplify the 1 plus 0.045 over 2. It's going to give me 1.0225. You don't necessarily have to do that. Sometimes those decimals are going to be gross. We can type it in as an addition on there. We're not going to do as much of these with our logs and exponents and things like that the other way. To the power of 40. So type these into the calculator. What do we get? How much is in this account if she puts almost $5,000 in and then forgets about it for 20 years? $11,688.91. $11,688.91. That's a period. So that's a lot of free money. If you can buy in a savings account that's giving you 4% interest, put everything in it and don't take stuff out. So what if she found a better bank that had the exact same interest rate, but this time they were going to compound monthly? What is going to be different between this equation and this equation?
12.
The n. What was a 2 is going to be a 12. So everything else is the same. We're starting with the same $4,800. We're going to have our 1 plus. We have our same rate, which was our 0.045. It's just that our compounding factor, instead of being a 2, how many months and years? We have 12. So we're going to have now 12 times 20. What are we going to get? How much is in this account?
11,786.24 cents.
0.24 dollars. So she gets a couple about $100 more just by changing when the interest is calculated. So instead of doing 2 bigger chunks of interest, they're going to do 12 little baby chunks of interest. So we're going to see all kinds of different compounding units. Some of them are weird. Some of them are things that we know, like how many months a year, semi-annually. It's not super often. It's twice a year. Other ones that we will see often in problems, we're going to do with the next set just to practice this again. We've got compounding quarterly. And this one is again, and compounding weekly. Yes, that is separate. Yeah, the picture's on the next one. So, now we've got that Aaron has $5,200 on his credit card that charges 21% interest, which is a normal credit card interest rate for a new credit card holder. And we want to know how much money he's going to owe after 3 years. So he charges $5,200. He gets a brand new credit card after college registration, buys a PS5 and goes on vacation for spring break, and then forgets about it. And he tucks the credit card back in his wallet. He doesn't spend any more on it, and just keeps losing the bill. Like he put the wrong address on. There was some sort of mistake. So it's the one set of charges. How are we going to put this together? His initial charge, $5,200. Are we going to be subtracting? Is it going to lose value? It's going to cost him more money. It's still a plus, even though it says they're charging him interest. He owes the $5,200. He owes them interest, so they are both gaining. So be careful on that. It's still a plus. What's going to go on the top of my fraction? 0.21. What's going on the bottom? 52. There's 52 weeks in a year. So our exponent is going to be 52 times 3. So if we get to freshman orientation, get a credit card, buy a PS5, and go on vacation for spring break, and then forget to pay the bill, we will, for all of that, owe together $9,751.20, probably plus charges. Don't let your balance carry over on a credit card. If you can't afford to pay for it in cash, you can't afford it. It's not that you can't use it, but you need to pay it off as quickly as you can. The longer it sits there, the more you owe for something that you didn't get. Because that's an extra more than $4,000 that we got nothing extra for. That's a lot. All right, so last one like this, because I wanted us to see another compounding unit that we don't think of frequently unless we're in the financial sector. It happens a lot in financials and in business. Things will happen on a quarterly basis. Like you'll hear about fiscal quarterly reports. What is our compound factor going to be on this one if it's compounding quarterly? 4. That's the difference on this one. So we're going to have our 1 plus. It's just that our n is going to be a 4 this time. Everything else is staying the same. Everything else stays the same. It's just that we're compounding quarterly instead. So quarterly. So how much is he going to owe if he compounds the interest quarterly? $9,108.79. It barely changed. What's more important for our credit card rates is the interest rate, not the compounding factor. The interest rate makes the bigger difference. Okay? Questions on the compound interest stuff? Okay. There's a couple more types of questions in this section that we need to go through. They're a little bit weird, and they didn't really fit nicely anyplace, so they're just kind of tucked in here. So, what's up? I'm going to talk about the quiz at the end. I have a review. I've only made the answer key for the front side, so I cannot guarantee that the back side works properly, because sometimes chaos. But all right. So honestly, I want to start with the right one because it works. It's a little bit easier to think through, I think. So the y-intercept at 8 and goes through the point 3,1. So this is using kind of our most basic form of the exponential functions that we started with yesterday. Our y equals a times b to the x. Just because the left one has a k plus on the end. So what we have here, our a is going to be our y-intercept. So on this one, when x is 0, that's the other way to think about it. When x is 0, I know it needs to equal 8. So when I have a y-intercept at 8, that means I know for sure my x is 0. It goes through the point 0, 8. So 8 equals a times whatever the heck our base is to the 0. Anything raised to a 0 power? 1. So 8 equals a times 1. So what is a? A is 8. Look at the equation again. There you go. So now what I have is that my y equals 8 times b to the x. So now we need to figure out the base, and I know it goes through the point 3,1. So again, we're going to have our 1 equals 8 times b to the 3rd. Substitute that point in. We want to solve for b. What do I need to do to get b by itself? Divide by 8. I have 1/8 equals b cubed. What cubed gives me 1/8? 1/2. 1/2 cubed gives me 1/8. Because 2 cubed gives me 8. But This isn't just 8, it's 1 over 8. So I need 1 over 2 to give me 1 over 8. So we're going to have to logic our way through this until we get over into logs. So most of the time, they're not going to be quite that fractiony. So our base is going to be 1/2. So the equation that fits this is 8 times 1/2 to the x. So that's how we can write the equations when we're given points. The one on the left is really similar, except it has one additional piece in there because that has a vertical shift. We're going to approach it the same way, though. It's hard to see because the picture's all black and white, but in this picture, we have an asymptote right here. At y equals 1, we have an asymptote. So this one has the starting equation that we're going to use of y equals a times b to the x plus k. And k is our vertical shift. So I've got 2 points on my picture. They're labeled. I go through the 0.05 and I go through the 0.17. We need to fill in the pieces. Start with the asymptote. Our vertical shift, our asymptote, that's going to happen where? 1. K is 1. That's what that means. The K is our vertical shift. Our K is our asymptote. So this is the same thing as y equals a times b to the x plus 1. We're going to go exactly through the same order we did before. I have an x of 0, so that's going to make it easier for me to find the a. So I'm going to start with this one, my 0, 5. I'm going to be a little tight on space, but that's okay. I'm going to write small. So I know my y is, not that pen. My y is 5 when my x is 0. So 5 equals a times b to the 0 plus 1. We're including that asymptote there. Anything raised to a 0 power is 1. So this becomes 5 equals a times 1, which is a, plus 1. So what is our a? 4. So then we're going to do the same thing just with our next point, my 1, 7. So my y is 7, and our a is 4 times the base to our power here. Our power is 1 plus 1. So we're just taking the points we have and kind of substituting them in to find the thing we need. So what can I do to figure out what b is? Subtract 1. So I've got 6 equals 4 times b to the first, which is the same thing as just b. So what does b equal?
3 over 2.
Yeah, divide both sides by 4. We're going to get 3 over 2 is our base. Oh, my phone just chirped. Oh, because it's about to rain. So our equation, I'm going to be right at the bottom down here. Our y equals our a of 4 times our base of 3 over 2 to the power of x plus 1. So when it has that asymptote, it just gives you a k on the end. Dude, it's 9:34. We're not done. Nice try, though. Okay. Because there was one more kind of interest that we worked with before, but it involved another piece that we needed to talk about. But questions on this before we go back towards interest problems? Because we're going to touch on the graphing a little bit later. I want to do all the graphing at once. Because we have one more piece we need to talk about with interest that's going to come up again throughout logs and all those things. And that's E. E. PERT. PERT. Because we have our continuously compounded interest. Because banks would like to charge us as much interest as possible on our credit cards because they really, really, really want more money from us. So E is a number. It's like pi, but used less frequently. It is a button on the calculator. It is the second function above the natural log. So right above the ln is our E. It's about 2.718 blah, 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 blah. It's one of those never endings, just like pi. I'm not going to ask you to ever recite it for me. It's not a thing that we need to do with it. It's just something we have in the calculator. But it's used a lot with our compound interest, and it's going to be used a lot in logs, and we're going to see it in solving stuff. So we're going to start with a compound interest problem. It is just like the compound interest problems we did before. We're just using this formula. It has the same rules. Principal is still our starting amount. That's the P. E is that Euler's number, that E. That is a button on the calculator. Our rate still needs to be as a decimal. Our time is still a unit of time. They're just both in the exponent now. So when we put this one together, how are we going to write the equation for Miss Amy here? What are we starting with? $5,000. That's our principal. I know I didn't print this one out. So we're starting with our $5,000. The next thing in our formula is the E. We will always have an E there for our compound interest. E is not a variable. It is a number just like pi. Do not substitute anything in for E. E is E. Just leave it as an E. In our exponent, what are we going to have? Gorgeous. 0.046. We scooch that percent as a decimal. Times 18, our time. And then we type this into the calculator. I'm going to do this one in the calculator on the screen just because the E is in kind of a funky place on the other calculators and I want to suppress it. So there we go. So we start with just putting in our 5,000. To get to the E, you hit the second button, and then you hit our natural log. It gives us our E and kicks us up into the exponent already. It knows we're going to put a power in, so it just has us do that. And then we can put in our 0.046 times 18. We can do that operation in there. We don't have to simplify it. It'll do it for us. Where are we going to round? We are in money. So 2 decimal places. So $11,443.68. $11,443.68. So it's really, really similar to our other exponential equations. E is just a number. It's a button on the calculator. Which means when it comes to solving stuff like we did yesterday, it's going to be about the same. Let's do both of these and this will be it. We can do this. Yes, we can. What's up? Yes. Last two. So e to the 4th to the x times e to the x squared equals e to the 12th. When I have a power raised to a power, what do we do with those numbers? Multiply them. So this is e to the 4x. When I have bases that are multiplied together, what do I do with those exponents? We add them. So this is e to the 4x plus x squared equals e to the 12th. What do we do here? Ooh. The bases are the same. I don't need the bases anymore. 4x plus x squared equals 12. What do we do? Subtract 12. Scoot things around so we're in standard form. X squared plus 4x minus 12 equals 0. Yes, I did it wrong in my book. Love that for me. I did 6 and 4. So our factored form here, because we could factor this, we would have a positive 6, negative 2. So our solutions here are negative 6, positive 2. We can solve with e. This is something that people get stuck on sometimes. How could I make these have the same base? Yeah. How do we make a fraction not be a fraction? Negative exponent. This is the same thing as 3 to the x plus 9 equals 3 to the minus 1. 3 to the minus 1 is 1/3. 1/3 is 3 to the minus 1. So this is the same thing as having our x plus 9 is negative 1. What's x? Negative 10. Okay? We did not quite get through everything in both 5.2 and 5.3. So, the quiz will not be until Monday.
Thursday?
Monday. Literally just wrote Monday. Literally wrote Monday. I do have the review. If you'd like the review to have it today, I have them here. I'll put them on the table at the front so that you can grab one on your way out. You'll also be able to pick them up tomorrow. But just since we're not getting through everything we need to, I'm not gonna change you're going, right? Okay? So because we have a little bit of graphing that we need to talk through. We read graphs, but we haven't made any graphs, and I don't want us to have to try and figure that out on our own. So tomorrow we'll do a little bit more solving, and then we will look at graphing. And then we probably will get to start logarithms before we get to